The last speaker of the session, Professor Gleb Sukhorukov, who is the chair in Biopolymers and Bioorganic Interfaces at the School of Engineering and Material Science of the Queen Mary University of London, UK. And soon your first slide will be on, but basically Professor Sukhorukov will be talking about the formulation and synthesis of different type of capsules and nanoparticles that can be used for different applications. It will be focusing more on the basic science aspects of the problem, so the synthesis, rather than its clinical translation and application. And good enough. I was running out of words. Go ahead.
Yeah. So thank you, Chairman. Well, I don't have just to repeat my title then. So what actually I'm going to talk to you today, it's in one side, it's just like new life in this old story, just about encapsulation. And another thing, what actually I was pretty much pleased to hear this session that the first talk presented by our chairman, just making those type of structures using just photolithography approaches and make just like templates to make the films that actually you could load with different chemicals and release it in the right moment. Okay, first about just new life and old story about the capsules. I have to say that we are interested in remote control, and being a physicist by my education, I always look about what physics could actually offer us to make our capsules remotely navigated. And from physical, it's just magnetic field, optical addressing, ultrasound, and also alternative magnetic field in a different different frequencies, because it could be hypothermia effects and also could be just like vibration effects in the low frequencies. And then how just to build the structure and of those vehicles, and the best way they have to keep the responsiveness, and how actually could make your capsules multifunctional is just if you use so-called layer-by-layer approach. I don't have just to tell you about how just to make this layer-by-layer capsules. It's widely published. There are also a lot of the reviews about this. But so far, you actually could make the capsules of that size. I mean, there is no actually upper limit. You could use it. You just need two components, two polymeric components, that are actually capable to make stable bonding, either with charge interactions or with just hydrogen bond interactions, and actually could be done fully out of FDA-approved materials. But what we are interested more is just to remote activations. The first of all, that means magnetic delivery, and also use different particles here that actually capable to harvest light, like gold, carbon nanoparticles, or actually silver. And we don't do much just targeting by chemicals. So we make those capsules, and we're interested in how they actually behave in vivo. And to do this, first we make the experiments on the glassy capillary. We have the blood flow rate on the same as were actually used in the vessels, 500 microns per second. And we make our capsules labeled with a fluorescent light and also with magnetic field. And if you apply the magnet, you actually start to collect your capsules near the wall. We actually put the magnet. If you remove the magnet, whatever capsules you have, you actually to wash it out with the blood flow, which is actually no surprise. There is nothing on the glass wall that actually could keep your capsules if you actually remove the magnetic field. The situation is pretty much different to in vivo. And the problem in vivo is that you have to put your magnet near the vessels. At the same time, you have to look at you build your optical systems to see your vessel. And to do this, you have to really do the operation. Well, we use the mesentery. And here, so this is just red. So we actually put their optical systems, a magnet in there. So it actually looks like this. And I have to say that actually could see the flow of our capsules in vivo. I hope the video should work. It should work. Yeah. Yes. So what actually we see here, so these are our vessels, and what actually you see now in the first moment is just a flow of erythrocytes. Flow of erythrocytes, you put the magnet, okay. You still have your flow of erythrocytes. If you switch it to fluorescent light first, you see nothing. It will happen just in a few seconds. You see nothing. And then for the catheter, you have injecting here our capsules. And I hope you will be able just to see it in a minute. Yes, this is fluorescent stuff. This is actually our capsules. And then they actually, especially the site of bifurcation, you have a collections of your capsules. And the question is, do they block the blood flow? And if you switch it back, in a second, you'll switch it back to transmission light, and actually it could tell you what actually happens. And your so you see, now you still have continuously flow of your electrocytes. We did the histology. I didn't show here because of the time, but in histology you could find that your capsules get into the wall of the blood vessels, and they actually still keep the erythrocytes flow. Well, we also have done experiments on the mice. We have injected the capsules, magnetic capsules in one leg. We put the magnet inside the bioluminograph, and actually you could recognize it just simple. What actually we found, it's just fridge magnet. You can't do much about this. This is just a lever, it takes the most, but still you have some, we actually found up to 8% of capsules being localized near opposite leg just using the magnet. So this was just about the capsules. So mice was actually survived the 3 days after. It's still fine, and all the materials were just degraded, and mice was survived well. So another story with those capsules, because those capsules can be internalized with the biological cells. We use different cell types, and one of those was also mesenchymal stem cells. They're actually capable to internalize those capsules that they get on the surfaces, and eventually you could find up to 30 capsules per cell. And if you have, for instance, a ratio, say, even 20:1 capsules, your cell is still viable. You actually could see it in the confocal microscopy. They're actually inside. And the interesting thing is, it's like an anchor. If you have the capsules inside, your cell becomes magnetic. And for instance, if you initially have, for instance, mixture, the gray is the cells, green is the capsules, you pass it through, you actually could separate those cells which actually have been capsules inside. And after those manipulations of the mesenchymal stem cells, the question is whether the ability to differentiate changed after manipulations with the magnetic field. And at least we found for normal MSC cells, if you actually induce the epipogenic differentiations, whether you do have those capsules or you don't, you still have lipid vacuoles formed. Or, for instance, for transformation to osteoblast cells, they both, control samples and also cells with our capsules are still capable to produce calcium deposits. So what actually, simply speaking, is that at least in vitro, we show you could make their cells magnetic and actually could move it as a magnet. And what you also could do, for instance, you actually could encapsulate mRNA, which actually cause GFP protein synthesis there, and then actually you could make the separation, and only those cells would actually eventually took our capsules inside and actually transformed to be green, and then you still have they are magnetic, so actually you could separate them. So your cells could become magnetic. And now I'm just coming to the last part of my talk, and we use this type of their template. Well, actually you could do it now with a PDMS template. You could make the film, remove the template, and actually get various type of the structures. All depends on your initial template. What actually I want to say, out of just polymeric films or out of different polymers, you could make those, as we call it, chambers. And those chambers you could load. And one of the way to load them, for instance, if you coat it, for instance, with polylactic acid, right, or with layer of PLJ, which is actually hydrophobic, the simplest way is you pour the drug or active material solution. Your drop will be just, once it's dried, it just gets broken. It's hydrophobic and gets broken into small wells here, dried there, and then actually you could put another layer, like laminated, and make actually your chambers. And so far you could put there, for instance, sodium chloride crystals, adrenaline precipitates there, different type of dyes. And once you actually laminate it, because it's hydrophobic, it's inside you have your air bubble. It actually is air bubble. That's why if you put it in the water, it becomes it doesn't become soluble because your water-soluble precipitates is within micron-size air bubble. And you could make those coatings on the different type of stands or any type of the surfaces. And whatever you actually want to put it in, we actually could make it. So you have your air bubble within your chambers with some precipitates inside. And what is actually the most sensitive to the air bubble? It's ultrasound. If you apply the ultrasound, for instance, if you have a focused ultrasound, whatever area is subject to the focused ultrasound, is actually you blow up your chambers, and your precipitates will be dissolved. So you actually could make those films freestanding. You could put it under the, for instance, operation. You could put there, and either it will be just degraded in a longer time, or actually you could simulate those release. So in the end, I just have 2 seconds left. I have to thank the people in the Queen Mary Nursery of London, also in Saratov State University, who intensively collaborate, and also in other places, and also the funding. And thank you for listening to me.
Thank you very much, Gleb. So, questions for Gleb? Here we go.
So, thank you. So maybe I missed this, but what's the size of these capsules you used then to integrate into cells?
Yeah, I mean, well, the capsules was just starting from 50 nanometers and up to, there is no upper limit. And once what actually I showed to you, it was a few microns. The cells could take the capsules up to the 4 microns inside. If it's just 10 times bigger the cell, the mesh you could take. The smaller they are, the more difficult to work with.
With ultrasound, yeah. Okay, is there any other question for Gleb? Good. Oh, please, Wafa. This is the last speaker, so.
What's the size or the diameter for your microchambers?
Well, this is as well as photolithography could help. I mean, the modern methods of nanoimprint, it could go down to 100 nanometers. We don't need that small. And those what actually I showed, it was about 5 microns. But that's actually you easily could do. It's almost like it's on production line for various things.
Okay, we thank again Gleb, and with this we also